Relative atomic mass is a way of comparing the numbers of atoms of different elements by looking at the relative masses of those different elements. It has symbol A subscript R, and we can describe it as the weighted mean mass of one atom of an element. We take the weighted mean mass of one atom of an element to take into account various different isotopes of a particular element and compare that against the mass of 1/12, the mass of one atom of carbon-12. But of course, relative atomic mass really involves weighing these particles. So how do we go about weighing the one atom of an element, or even one atom of carbon-12? Well, one way of doing it is to use a mass spectrometer. So a mass spectrometer can be used to determine the mass of particles, or more specifically, it will separate ions out with different mass and detect them. Now, the major use of mass spectrometry is to identify complex molecules, but we will be considering that aspect of mass spectrometry at some other point. What we're going to consider now is how a mass spectrometer actually works. Now, you'll get a walkthrough of the mass spectrometer later in this movie, but you have various different processes occurring in the mass spectrometer, and you need to remember these. Firstly, vaporization. We need to get our particles in a state where they are completely separate and can move around freely. Second step, ionization. Ionization involves knocking an electron out of an atom and enables us to actually manipulate our particles. We're going to accelerate our particles along an evacuated tube and then deflect them and detect them. Let's have a look at these in a little bit more detail. So, vaporization to begin with, the sample needs to be in a gaseous state, as I've already said, needs to be able to move freely. Generally, the sample can be put into the mass spectrometer as a vapor or may need to be injected initially into an oven to vaporize it. Ionization, as I've said, to manipulate our particles, they need to have some sort of charge, and we do this by using an electron gun. This electron gun fires high energy electrons, knocking out an electron from our gaseous atom. And there's the equation that we have. Now, we can knock more than one electron out of our atom, but generally you tend to knock only one electron out. Acceleration. Particles are accelerated by an electric field which consists of a series of increasingly negatively charged plates. Remember that our particle is positively charged. They'll be focused into a beam and into a fine beam after the acceleration, ready for. Now, deflection is the key to how a mass spectrometer works, and the particles are deflected by a strong magnetic field. Now, this is produced by an electromagnet, which can therefore vary that magnetic field strength. Now, the degree of deflection depends upon the mass to charge ratio. If you think about it, if you have a big heavy particle, then that will be deflected less, whereas if you have a highly charged particle, that will be deflected more. So therefore, if you have a small mass to charge ratio, in other words, you have low mass, big charge, that's going to produce a large deflection. On the other hand, if you have a large mass to charge ratio, in other words, big mass, small charge, you will therefore have a small deflection. Now, generally, of course, you will find that most of the particles passing through the mass spectrometer will have a +1 charge, so that Z will always be equal to 1. But occasionally, you will find that that Z will be 2, and therefore what you will find is that the degree of deflection will be different for the differently charged particles. Finally, detection. Now here, of course, our particles, our charged particles, have been deflected by just the right amount by the magnetic field to pass round the curve of the mass spectrometer, and they will hit a detector which will be negatively charged. Remember, our particles are positively charged, so they'll hit that negatively charged particle, picking up an electron. And of course that means that the electrons will shuffle along the wire, creating an electric current. Now, it'll be a very small current, but the size of the current will depend upon the number of particles hitting the detector at a particular time. But that current can be amplified and then either sent to a computer or sent to a chart recorder and displayed as a spectrum.